Hello everyone, I am Deep and I am going to present adversarial scene editing automatic object removal using weak supervision. This paper was accepted to NeurIPS 2018. So the goal here is that given an input image and some image level supervision, we want the model to automatically remove the given object from the image. So you have an image and a target class. You would want the output image to look something like this. So what are some problems with current works? So while the progress is remarkable, it has been limited to single object centric images like faces or constrained images like street scenes from a single point of view. So there is no work on there is no good work on scene level images. While there has been some work, but the image quality is relatively significantly mediocre when compared to work with object centric datasets such as structured faces. Also, the majority of work for object removal focuses on improving the in-painting part, while this paper also focuses on the object mask segmentation. So what is the paper's contribution? The paper proposes an end-to-end editor model which learns to automatically remove objects from a given input image provided with supervision, such as image labels and unpaired data. The editor model proposed achieves on-par performance to fully supervised segmenter methods such as mask RCNN. So here is the bird's eye view of what the editor model looks like. The editor model is a two-stage editor model where the first stage is the mask generator and the second stage is the image inpainter. It is worthy to note here that the model also takes the target class label as input because this was not mentioned in the paper's figure. The mask generator in stage 1 learns to locate the target object class in the input image and masks it out by generating a binary mask. So given the image and the target class, the mask generator will generate a binary mask. In the second stage, the image inpainter does two things. The first one is it does the inpainting, and it also learns to optimize that the output to make it look like a realistic output. So Y here is the output from the inpainter. This is just the colorized version of the inverted binary mask. This is the inverted binary mask. This is the in-painted part of the in-painted image. How does the architecture of the mask generator look like? It is just a modified version of VG19 which has been pre-trained on ImageNet. The last two max pooling layers have been removed. So yeah. And they also removed all the fully connected layers. On top of that, they add 3 con layers. Also, throughout the paper, the notation trend, and throughout my slides, the notation trend will go something like this. C stands for the con layer, the subscript stands for the number of filters, the superscript stands for the size of the filters, L stands for leaky ReLU, 0.1 is the negative slope, and R stands for residual block. I'll get into what a residual block is in just a moment. So they repeat the very same block 3 times with a decreasing amount of filters. And finally they have a con layer with sigmoid activation function at the end. Here the residual block is just 2 con layers with instance normalization. I here is the instance normalization. Now let us go into detail of what the architecture of image inpainter looks like. It is just a combination of 3 blocks. The first one is downsampling block, a bottleneck block, and an upsampling block. The downsampling block has a con layer in the start as an initializer, then has 3 downsampling blocks. Here D of 2 means it is just a con layer with filter size 4x4 and a stride of 2, which halves the spatial dimensions of the input. So if, let's say, here the input was 64x64, the output would be 32x32. The bottleneck block is just 6 back-to-back. The bottleneck block is just 6 back-to-back residual blocks. I cannot see the pointer. Okay, no worries. The upsampling block has 3 layers of upsampling. This is the first layer, the second layer, the third layer. Here U of 2 is just a bilinear upsampler, and finally it has a con layer with hyperbolic 10 as the activation function in the end. It is important to note that this uses the hyperbolic 10 as the activation function and not sigmoid, the image inpainter. Here U2 is just a bilinear upsampler, which will double the input dimensions. So how will we train the editor model? So let's first talk about training the first stage of the editor model, which is the mask generator. The mask generator is trained to fool the object classifier. So the mask generator here in red is only trained to fool the object classifier. Object classifier here in this case is a modified VGG19. I won't go into details of what the architecture of object classifier is, because it is not integral to the model, but it just classifies if there's a person or not. So this is how the loss function for the mask generator looks like. D of CLS is the object classifier score given an image and the target class, if there is a, in this case, if there is a person or not. So how will we train the image inpainter? Image inpainter is only, here in blue, is only trained to fool the real fake classifier. The real fake classifier here is an adversarial loss, D of RF. I'll explain in detail of what D of RF is in coming slides. So if the editor model only has the input image and the target class as the input, how does it learn to locate where the object is? The answer is a prior mask distribution. So the editor model will take in a prior, here there is prior, so the editor model will take a prior distribution which the mask generator uses to locate where the object is. We can impose 2 kinds of prior to the editor model. The first one is unpaired data, such as segmentation masks from a different data set. They use Pascal VOC in this case. If you don't have unpaired data, you can use simple geometric shapes such as randomly sampled rectangular boxes of different aspect ratios and sizes as the prior distribution. So the masks generator, the masks generated from the mask generator go to a new mask discriminator. This is the prior mask distribution. This could be from unpaired data, or they could be randomly sampled geometric shapes. So how will we train that mask discriminator? You will minimize the Wasserstein distance between the prior mask distribution and the masks generated from the mask generator. So this is how the loss function for here this is a Wasserstein GAN. So the mask generated from the mask generator will go to the discriminator, and the mask generated, used from the prior will also go to the discriminator. You would want to minimize the Wasserstein distance between both the distributions, and this is how the loss function for the Wasserstein GAN looks like. So given a class specific prior mask distribution, we assign high scores to the samples from the prior distribution and the mask generated from the mask generator. The mask generator will also be additionally optimized to fool this mask discriminator, because we want to create we want to generate realistic masks. So this is the L prior we will impose on the mask generator. So how does the final mask generator function look like? You have the initial object fooling classifier plus the adversarial prior. Also, you would not want to have big masks, because in that case what the GAN will try to do, it will just try to add adversarial noise and try to fool this object classifier. We don't want that, because the task at hand is image inpainting. So they impose a size regularizer where they control the size of masks. So minimizing this, you would want to have not very big masks. So this is how the actual final loss function looks like. The initial object fooling classifier plus the adversarial prior plus the size regularizer and hyperparameters to control all of them. How will we optimize the inpainter to produce a realistic looking image? So what they do is they the image inpainter basically reconstructs random patches fooling the adversarial real fake classifier. So the image inpainter here in blue fools the real fake classifier. They incorporate the reconstruction loss, because again the task at hand is inpainting. So the reconstruction loss for inpainter would be standard L1 plus a perceptual loss. Here they if let's say the newly generated inpainted image and the original image, if there is translation variance between both of them, something like standard L1 loss would have, it would be very drastic. That is why they include perceptual loss. So they input both the images to a of the book network, and they compare feature maps. So you could preclude the something like translation invariance. As only a small percentage of the realistic, output image would comprise of fake pixels of the real fake classifier generated by the inpainter. It is a very hard task for the classifier, the real fake classifier, to find the very few pixels that contribute to the global GAN loss. So they overcome this by incorporating local pixel level labels to the entire image. So this is what I mean. In a standard case, the network would say real or fake for the inpainted image. Here what they do is they have local pixel level labels for each pixel. So each pixel would say fake, fake, or real, real, or whatever. So instead of one global label, they provide local pixels. Why? Because global GAN loss produces smooth and blurry results, whereas the local GAN loss would provide sharp texture rich images. How will you provide local pixel level labels to the image? So what they do is you obviously have the inverted binary mask in this stage. They will assign all the pixels in the inverted binary mask as real, and after the inpainting, they assign fake labels to the inpainted pixels, and they would calculate least square loss. Here they have a least square GAN. So the loss for least square GAN looks something like this. you have the loss for real pixels. If you remember, you had hyperbolic 10 for the inpainter, right? So here in this case, the -1 is -1 and +1 is because we have a hyperbolic 10 as the activation function. This is how the loss looks like for the real pixels. You would want to maximize this, and you would want to minimize the fake pixels. To better match the textures in the inpainting output of the input image, and they incorporate the style loss, and they also include the total variation loss because it helps to produce more smooth boundaries between the inpainted region and the original image. So this is how the final loss function for image inpainter looks like. The first real fake classifier, then you have the reconstruction loss, the total variation loss, and style loss. The total variation loss and style loss have basically been borrowed from NVIDIA's latest StyleGAN paper, and you have hyperparameters to control all of them. So keeping the goal of performing removal on scene level general images, they train and test their model on MS COCO, as MS COCO contains significant diversity within each object class. So they also do some pre-processing on MS COCO. So if the target class occupies more than 30% of the input image, they remove out that image. For the prior mask distribution, in this case for MS COCO, they have there are 20 shared classes between Pascal VOC and MS COCO, such as person, aeroplane, boat, and things like that. So they use Pascal VOC as the prior mask distribution to the mask generator, and they resize and do some augmentation to the to both data sets. The input images have been resized to 128 by 128. To demonstrate the application of their editor model for content filtering, they show that their model can generalize beyond just MS COCO objects and can learn to remove different image entities such as logos. So they train and test their model on the task of removing logos from natural images from the Flickr's logo dataset. This is how the Flickr's logo dataset looks like. It is worthy to note here that the dataset also has some random images where you don't have any logos in the image. I think it is like 2%. For this case, they use the randomly sampled rectangular boxes as the prior mask distribution to the mask generator. Here they also the randomly generated rectangles are of different aspect ratios, areas, and also they do some rotations. They have 3 evaluation metrics. The first one is removal performance. How good did the model perform? How good is the image quality? And they also evaluate, they do human evaluation. So for removal performance, the removal success rate should be, we should be looking to maximize the removal success rate. We should be looking to minimize the false removal rate. For image quality assessment, peak signal to noise ratio is one of them. So peak signal to noise ratio has minimum, mean squared error in the denominator in its formula. So you would want to minimize loss, and in that case, peak signal to noise ratio, better peak signal to noise ratio, better the image quality. So low the error, high will the PSNR be. As peak signal to noise ratio is, outdated, they also incorporate structural similarity index. Structural similarity index just quantifies what the image quality degradation caused by the processing is. For example, it could be something like data compression or things like that. And obviously you have the perceptual loss where you compare two feature maps. You would want to minimize that loss, obviously. Also, they do some experiments with humans where they obtain human judgments on how their editor model performed. They show 100 randomly edited images to 3 separate judges, and they only considered the edited image to be successfully edited if and only if all 3 judges gave it a score of 1. So here are some quantitative results. There's a disclaimer. Since there is no prior work which proposes a fully automatic object removal solution, they compare their model to a standalone fully supervised mask RCNN based segmenter method. So what they do is they will use segmentation masks from a method like mask RCNN, and they will use their pre-trained inpainter to do the inpainting. So the disclaimer here basically is that inpainter used for every experiment is their own inpainter. So you have the ground truth masks for MS COCO. You have segmentation masks from fully supervised mask RCNN, and this is their model. Please note here that the mask RCNN method uses more stronger supervision because it has in terms of like object localization and object segmentation. So as you can see, the removal performance for their model is the best, but the drawback here is, the drawback of weak supervision is you don't have segmentation masks here, right? So the drawback here is that masks do not accurately overcome the quality, the quantity of where the object is. So the masks are a bit larger, which leads to higher false rate, which we would want to minimize. Obviously, for ground truth masks, the false removal rate is the minimum. And the same goes for image quality metrics. Obviously, for ground truth masks, the image quality would be the best. But as you can see, the performance of fully supervised based mask RCNN and something like their model, which uses weak supervision, is, they achieve on-par performance. Here I would also like to mention that the ground truth masks, the ground truth and the mask RCNN mask for segmentation are too close to the object boundaries, so they tend to leave silhouettes behind after their removal. I will show you some qualitative results which will clear things up. So they also study the effect of different priors. So let's say if this is the input image, if you have no priors, the segmentation mask would look something like this. If you randomly sample rectangular shapes, geometric shapes, so the box prior would look something like this. And this is how, if you use unpaired data, the segmentation masks will look something like this. So Pascal N, 10, 100 and all uses n randomly chosen unpaired segmentation masks for each class from the Pascal dataset. So using only very few segmentation masks from the Pascal dataset for the case of person leads to a drop in person removal success rate, because the person class is very diverse in MS COCO, and it has it has diverse shapes and varying poses and scales. So eventually, if you increase the number of masks in for the person class, they increase. Obviously, why is the performance for no prior best? Because when you have no priors, there are a lot of areas in the segmentation masks. So the mask basically is a very big mask, so the removal performance is high. But as you can see, the image quality metrics do not hold true. So the image quality metrics suffer if you don't have a prior. as the masks are very high. The same goes for mask accuracy. So the Pascal all version, offers the best trade-off between the removal performance and the image quality metric due to more masks for each target class. Here are some qualitative results. So this is what I was talking about. When you have a segmentation mask from a fully supervised method, they tend to leave silhouettes. Can you guys see that? They tend to leave silhouettes. So the image quality metrics suffer for fully supervised based methods. Same in this case. This is their model. These are the qualitative results on the Flickr's logo dataset. Here I would like to mention that quantification is a big issue. So let's say if the target class is Pepsi, where does the logo for Pepsi begin and where does the logo for Pepsi end is a problem for the the model. So it also tries to inpaint E, which should not be the case, but in this case NBC should be inpainted or shouldn't it be. It is highly subjective. So quantification, as I said, is an issue, but here in this case it effectively removed the entire BMW symbol. So here are some failure cases. So as you can see, if the target class occupies more than 20% of the image approximately, their editor model fails. But here in this case, this I think hardly occupies 5% of the image, but still this did not pass the human evaluation test. So these are some failure cases. Again, as I said, quantification is a big issue. There are 2 boats here, but the editor model only removed 1 boat. Again, quantification, there is a person here, it effectively removed the person, but there are also some people standing behind the person. The editor model should remove those persons as well, but it didn't. And again, quantification. So here horse was the target class, but it also removed the people sitting on the horses. So they are treating this as a failure case. They conduct 2 ablation studies. The first one is joint optimization. I didn't mention. The entire training process is done in alternate epochs. So firstly the mask generator is trained, then it is hold fixed, then you train the image inpainter, and at every alternate epochs. So they try to do an ablation study where they do joint training, and as you can see, not surprisingly, the in-painting quality is better. So they conclude that joint optimization is beneficial to the editor model. Interestingly, the mask generator also, the performance also increases the mask accuracy. So the second ablation study they do is they try to mix and match some in-painting components. So something like the total variation and style loss, and they also do some experiments on the global GAN label or the local pixel level labels. So as I already mentioned, global GAN loss produces smooth blurry results. So it is evident the image quality metrics are better for global GAN, whereas for local GAN the loss is better, the perceptual loss, but PSNR and structural symmetry index suffer. So in summary, the editor model proposed is an automatic object removal model which only uses image level labels or unpaired data as the prior, and it achieves on par performance with fully supervised segmenter based methods such as mask RCNN. Thank you.